Okay, welcome everybody to the first edition of Integrability Journal Club this year. And I'm very happy to introduce Paul Fendley from Oxford, who will tell us about integrability from braided tensor categories. Please, Paul.
Oh, well, pleasure to give a talk in the seminar. I've enjoyed the ones last year, so happy to start the new year. What I'm going to talk about is something that I've been, why I put it long last here, is something I've been talking about for a long time, but I think this might be the first time I've ever given a talk on this work. After I wrote the paper, it took a long time, but there's a paper from last summer, and so there it is. And anyway, so what I'm going to talk about is, I think, a very basic thing about integrability that I don't think was really known. Some, obviously, a lot of the story of, well, I'll tell you about will be known, but I mean, I'm trying to get at some, what I think are some really interesting questions about just why models are integrable and what are the kind of basic characteristics integrable models have. Now, this may sound like something totally different, but it turns out, and I'll try and explain a little bit how, because the work I'm doing here is closely related to another epic saga on topological defects that I did in collaboration with Aasen and Roger Mong. I'm not going to really talk about that, but I'll put a plug in for at some point. But a lot of the techniques are underlined, and I'll explain why topological defects has something to do with integrability itself. So anyway, so now here's a very old story, which was that many interesting 2D stat mech models can be described in terms of not in link invariants. And this was a big thing in the 80s, and I'll again give you some of that history in more detail. But I think at least in the integrability world, at least based on my interactions with experts on integrability, most people don't really think about it. Even those of us who were around then, I was a grad student, I was paying attention to stuff. The people who came of age after that, again, maybe vaguely aware, but haven't really paid much attention. Now, in another world, in another part of the physics world that I sometimes hang out in, is this world of topological quantum computation. And so people started talking about not invariants for what seemed to be different reasons. But one of the things I'll try and explain is it's actually not that different reasons. And all the things that we've learned in the course of topological computation, and more importantly, the things that mathematicians have learned in the 30-something years since this became fashionable in the 80s, have made us able to do lots of other things. So in any case, for the math words, the keyword is key pair words is a tensor category. That's the mathematical structure. Sounds pretty fancy, but I'm going to explain a little bit about how that goes. But again, this thing in red is the key thing. So it's a bunch of rules that allow you to manipulate graphs without changing associated topological invariants. And that's, well, one of the things I'm going to try and argue. That's one of the key things that underlies at least some of integrability. It's a key part of the story. And so the moral of the story, and today and always in my life these days, is to draw pictures. Okay, so let me explain what I'm doing. First, I'll tell you what a fusion category is. It's really not that complicated, despite appearances to the contrary. Then I'm going to explain to you this old 80s stuff on how to define lattice models using fusion categories. And there's three types. Mostly I'll be drawing pictures, so I'll be talking about geometric models like loop models. But one of the things I want to emphasize, I'll say it for the first time, and I'm going to say it again because it's really important, is that everything I say can be converted through the miracle of all of this, mathematical technology into statements about local models like the Aasen model and Potts models and all your favorite models. So that's really important. So I'll usually be drawing the pictures in the geometric language, but I'll indicate later on precisely how the two are related. And another one that's probably the most interest to condensed matter types are these quantum Hamiltonians. And the observation I made has been rebooted, if you wish. When people talk about an any on chain, they're doing what I'm doing. It's the same. It's exactly the same thing. Just it's a different and very useful way of thinking about it. Then I'm going to seemingly switch gears and then tell you some, again, old stuff, not from the topological community, but from the integrable community. And the algebra community, and talk about just what integrable lattice models are with the Yang-Baxter equation. And since I'm in an integrability seminar, I can go really fast there, since I presume everybody knows that one. But if not, I'll tell you. And then I'll tell you something a little more elaborate. It's adding braiding to tensor categories. And that's a lot of review. That's pretty much, I think, all review. There, and that probably will occupy most or maybe all of the 45 minutes. At least that's my hope, that I'll be through all that by the 45 minutes, so we can take a break. Hopefully I'll be able to state my result before we take a break, and then after the break I can explain in more detail. And this is my result. I'll tell you what Baxterization is, but I'll tell you about a construction of fractional spin conserved currents. And then what I'll do is, using those fractional spin conserved currents, I'll give a simple formula for the Boltzmann weights that admit such conserved currents. And when I do that, I find, and this is not a proof, but I find in all the known examples where you can find these things, the ensuing Boltzmann weights also satisfy the Yang-Baxter equation. But one of the things I'll try and argue and try and show you is this is a much easier way of doing it than brute force Yang-Baxter solutions. And like I said at the beginning, I think it's kind of a deep sort of thing anyway. So, okay, so let me give you the background of fusion categories. Since I want to get through all this, I'll go moderately quick, but I do recognize this part probably not everyone, or probably maybe even very few of you have ever seen before, but the basics I think are pretty simple. So I'll try and say them pretty concisely, but of course, please interrupt if I say anything confusing or if I use some piece of jargon without explaining it. And so the basic idea of a fusion category is this beautiful thing. It associates a topological invariant. Probably topological invariant is not the right word. It's an isotopy invariant, but today I'm being a little sloppy. So you take some diagrams. So it's a graph built from trivalent vertices. And why it's not considered a topological invariant is because you put labels on them, these things there. And so, but when you specify a category, what you do is you say, here's the allowed labels. And in the category language, the allowed labels are called objects. Okay, so you get a labeled planar graph. You can do this on higher genus surfaces, but I'm not going to worry about it. And you make a labeled planar graph and allow only trivalent vertices. And so so in the category structure here, what it does, so what we get here is the sort of core to my thinking of a fusion category is a fusion algebra. So since most of the people here are physicists, think of like an operator product expansion, if you wish. These would be labels on the operators, and this is a fusion algebra, like the Verlinde algebra people call it, 2D CFT sometimes. So you just take a tensor product of these objects, and you get a linear combination of other objects, the C's, and then the coefficients are non-negative integers. So 0, 1, 2, etc. Everything I'll say pretty much just assume that those are either 0 or 1. And when they're non-zero, then what you have is a vertex that, like this, allowed in those pictures you draw in this thing I call the fusion diagram. And again, so anytime there's there, and if n is higher, you have to put labels on it. In more complicated cases, I also have to put arrows on it, but to simplify things, I'm not going to worry about putting arrows on today. So I've made, and there's a few other simplifying assumptions.
Oh, sorry, the alphas, betas, are these the same as A's and B's?
Yeah, yes. Sorry, I was too lazy to read the figure, but yes, they're just labels, right? Yeah. Sorry.
And then could I ask, so on this vertex, A, B is enter on different footing than C, or they're all on equal?
No, well, see, yeah, well, so with the simplifying assumptions I make, no, but there are more general things. And so, for example, you'll have to pay attention to doing stuff like this in the diagram. So if like that won't be the same as if it came in the other way and all that. So, but that's why I said I'm going to make some simplifying assumptions to consider only categories where you don't have to worry about this stuff. I'll comment again, but everything I say can be generalized to these more complicated.
Also, sorry, it seems you have also bivalent vertices on the graph. Yeah. How would you interpret them?
Did I? You mean up on top there?
Yes.
So I'm saying I'm making simplifying assumptions where there's just ignore that. In general, yeah, you have to take care of the bivalent stuff.
I mean, I thought you had to have different rules for these vertices.
Yeah, you do. Well, right, you get a factor. It's called the Frobenius. I mean, there's these annoying factors you get for. I mean, you still have them. So the point is, you have to orient something. So you say, now when I have something, so you have to pick it up, and then when you do something like I did up there, you have to you might collect some annoying factor. But there are many categories, all the ones I'll talk about today, for which that factor can be set to 1, so you can ignore it. But yeah, like I say, but yeah, that's
still only one label around this 2 vertex, or what?
Well, right. So even in the cases where I've made it more complicated, it's the same label. Well, it's that, and it's like particle anti-particle annihilation, because I've also thrown out the arrows. So what this really would be, think of it as if you think of these as world lines of particles, which is the enneon interpretation, you would think of that's like a and an A bar there, and then they're coming in and annihilating, and you might get a phase factor for that. So if you're doing this with arrows, then you would put an arrow there. And an arrow there.
Okay.
You can read that, sorry.
Fitness of number of objects is crucial.
The finite number of objects is needed to satisfy all the rules, and mathematicians prove lots of things. One of the things I put in my conclusion as well, physicists tend to not really worry so much about proving various general properties. And so if you look for like algebras based on supergroups, for example, you don't have a finite number of things, but at least a priori, I don't see any reason why most or even all of what I say can't be generalized. But the mathematicians like that, and it is very helpful for reasons that, well, it'll become clear as I go on. Great. Any more? I'll do SU2, of course. I'll give you one explicit example of this, SU2 level K. And the reason why I put SON here instead of SUN down at the bottom, of course, is again, so I can avoid arrows. SUN, you have complex representations in the Lie algebra, and the category, then you have to put arrows on things. But honestly, at least I'm pretty sure for everything I say, those are merely complications. They don't everything I said works. Okay, so let me give you an example of how you turn that diagram into a number. So again, with the simplifying assumptions, so I can ignore this data, these things called Frobenius indicators and stuff, really just a pain. There's basically 2 kinds of data, really just one, because there's the F symbols, and then there's the quantum dimensions. And these are just numbers, and I'll tell you what they mean. So what they do is basically allow you to manipulate graphs without changing the evaluation. So the evaluation is a number. Okay, so it's a number associated with one of these fusion diagrams. So with a fusion diagram, I mean this labeled graph that I talked about on the last slide. And so here's a simple one. So you just, when you have a bubble like this, so this is a sub graph of a bigger graph. And anytime you want to evaluate this graph, it turns into a number. So the evaluations of 2 distinct graphs that differ by having this and that will be the same. So you can think of this as you can get rid of this bubble. Well, the catch is A has to be equal to B for this to be non-vanishing. And then you get these numbers there, these things called the quantum dimensions. And so notice, I didn't say it, but I think it was on the previous slide. When you have the identity object, that corresponds to just no edge, if you wish, just omit the edge. So if I set A and B equals 0, means I just omit these edges. I have a loop, but then R and S have to be the same, otherwise there's no vertex. And then this formula just gives that a loop gets quantum dimension D, or D sub R. Sorry, I lost the R on that loop. That's labeled by R. Okay. So that's one simple rule. Now, obviously, this isn't going to do anything because you can get lots of graphs. So it's the F symbols that really allow you to turn these things R. And these are like basically glorified versions of 6J symbols from quantum mechanics or Lie algebras or whatever quantum group deformations thereof. So when you have this graph here, so you have 4 lines coming in, they fuse together. Well, it says you can relate anytime, again, you have this thing as a subgraph of a bigger graph. Well, I can re-glue them if you wish, or refuse them. And I get the same thing if I take the sum over all this intermediate label and then multiply by these numbers, these things called F symbols. So you can easily see again, and with the simple categories, I can just keep doing these F moves, remove bubbles, and I just finally get closed loops, but I can get rid of closed loops by that. And so I get a number at the end of the day. So that's what a fusion category does for you. It's a really remarkable structure. So let me give you an example of how to do something and show things. So, okay, so this is a graph, and all with the labels here. I've used both Roman, both Latin and Greek indices. And so the way you can evaluate this, I'll just say it in words, but so you would start like with doing an F move on this. So in other words, I think of those 4 as that, and then the A would be the one in here. And then I would go to something like that, then use bubble removal, and then you get that expression there. But I could have done it another way. I could have started, so let me, I could have started here.
Paul, sorry, could you do that a bit slower?
Oh yeah, sure. Well, let's do the second one now. I'll do the second one slower, okay? So I'm gonna take now this subgraph, which is chi, gamma, and then CB, sorry, not B, CA, right? And then that one is B. Okay, so now I can use the F move I put on the previous slide to do that, and there'll be a sum over that. That was the thing, was T prime. Sorry, I should have. And then there'll be some sum over them with those F symbols there, with all the external ones all still staying the same. Okay, but then you see if you draw the pictures now, it's going to be, well, I can try and do it. You'll get a bubble in the middle, which you can remove, and that gives you the quantum dimensions. But what I did, so there's 2 ways of doing this. The first one, and there's actually more ways. In fact, this thing has this is a tetrahedron. So this is called again, in the categories I'm assuming this tetrahedral symmetry. And so you'll see that any way you do it, you get all these identities for F symbols and quantum dimensions. And it's like integrability in that there's far more identities that you have unknowns, but the miracle is there's lots of examples of this. And so a famous one is the tetrahedral equation, which, since people are interested, goes like this. So you start with a graph like that. I'm not going to write all the labels, but hopefully we're confusing. So anytime it's an external label, it stays fixed. Internal, you sum over. And so then that we can do something like this. And then we can do something like that. Right. But instead of, I could originally have done these 2. If I wanted to do that, I could have then done now this. Okay, and it's not obvious, but if you look at it a little more, I can, let's change the color of the pen to make it more. So then if I do, say, on these, what is that? Yeah. Well, my pen doesn't want to do that color, so I guess I won't do that color. Anyway, sorry about that. So anyway, if I do that, I can get to that. So there's another one. And these make a pentagon, and that's why it's called the pentagon identity. So it's hard. So I omitted all the indices. It's horribly complicated. And for those of you who know about scattering, this is sometime when it comes up in the exact S matrices, I'll get integrable for a second. This is related to what people call the bootstrap equation for exact scattering, which, well, I could draw some more pictures. Ask me in the question period if you want me to try and explain that comment a little more. Okay, so I don't want to lose you, but so but hopefully that at least gave you the idea of what's going on here. So the miracle, like I say, is I view the category and all the data, these F symbols and these quantum dimensions as input. And so lots of people study these things. They're my starting point.
Sorry, just a question. You mentioned that this is called tetrahedral equation. In integrability, also we have Yang-Baxter equation, or there is also tetrahedron equation of the Mallochka.
Oh yeah, no, it's not. You're right.
It's unrelated, right?
Not that I know of. That's a good question. Actually, I don't know. Not that I know of.
So in the end, we may get something like Yang-Baxter out of all this.
Oh, no,
right?
we're going to get Yang-Baxter. That's the whole point of the talk.
Okay,
We will definitely get Yang-Baxter.
I think it is.
It has nothing to do with
analog of 6J symbol.
Yeah, the F is like a 6J symbol, or it's like a fusion code.
Yeah.
All right, good. Wait, how am I doing in time? So okay, good. Okay, so well, maybe I won't get through the first all this review stuff.
Sorry, Paul. Maybe just a quick remark. I'm just wondering: is this fusion categorical language has a relation or description in Bardism groups or not?
In what groups?
I mean, like board groups, like board 2 or board 3. Like this tetrahedron reminds clearly, I think, board 3. This is essentially this is a topological description of very much what like what you described.
Well, I'm going to go through the topological stuff. So I think probably that's what you mean. Anyway, I think that's what you mean. So we'll ask that again. If after, I think it's part 3, or is it part 4 of the talk? If it's not clear, ask again. Right, so, all right, so it's that, well, I'm glad that took longer because that, like I thought, was the part that to many of you probably wasn't familiar. So hopefully now you have a little bit of an idea. So now let me go back in time to the early 70s, Temperley and Lieb. Writing their classic paper that is, well, in integrability comes up all the time. But let me say what they were actually doing, because I think even among people who do integrability may not know. Definitely the people doing categories, even though they know Temperley Lieb very well, certainly don't, most of them don't know what Temperley Lieb were doing. What they were doing is trying to map different problems on top of each other. And so you can see in the abstract, they're starting with some graph theoretical problems. For people you know about chromatic polynomials or top polynomials, that's what this Whitney polynomial thing is there that I singled out. So, and for those of you know, oh, that's the Potts model. This is the paper, Temperley and Lieb, that proved this had something to do with the Potts model. In this original paper, they didn't talk about the Potts model, if I recall, but they talked about the 6-vertex model. So they're relating graph problems to there. And so what really they did was they showed how these transfer matrices of seemingly different models could be written in terms of operators satisfying the same algebra. And what's marvelous is with appropriate choices of the boundary conditions, the partition functions could be related exactly. And the even though boundary conditions are not always paid attention to, it's really important, and you get people use the word equivalent too much when they're doing these things. Anyway, so, but they're the same. Now, in one of these great coincidences of great minds, something in the air and these great minds coming up with deep results that are almost the same result through very different things. Notice again, 1971 in the sorry, what? My pen decided to stop working, but that's okay. There we go. That's my laser pointer. No. anyway, so in 1971, Fortune and Castelline showed another way to relate graph problems to local problems. And so this one is related to the pots, so the dichromatic polynomial and the top polynomials, all that stuff. And so they related graphical models to that. And the way they did it basically was loops. They didn't say it originally, but they talked about a random cluster model. And it's the same thing as a loop model because you just have loops surrounding the clusters. And so I thought it was historically important, and that's well known in the integrability community, but not known in the fusion category community. Basically everything can be put together. And this is what was done in the 80s. And again, these three kinds of models I mentioned before. So let me give an example to be very concrete. The loop model, in fact, the model that Fortune, Castelline, Kemper, and Lieber studied. I take a lattice. I drew it this way for later reasons, but it's called a completely packed loop model. So I have these loops that run along the edges of another square lattice. I drew the dots on the dual lattice, and those will come back to us. And every time, so on every edge, you have one of these loops, and every time they meet, there's two ways they can avoid each other, either horizontally or vertically. So that's the completely packed loop model. It's also the random cluster model. You would draw lines connecting those and all this stuff. Turns out it's not as obviously equivalent to the Potts model, but that's what Temperley, Fortune, Castelline did. And so the partition function in the loop language says you have this weight here, which is a number d to the number of loops. And then we have these local weights v and h. And they just count the number of this and that, the two kinds of avoidances. Okay, now this is a non-local model because to know what the number of loops is, you have to follow loops all the way around. So, there's, well, it's the way it is. And in general, this is the simplest and most important example of a whole class of models whose partition functions can be written in the form where the sum over all sum loop or geometric type configuration, and there's a topological weight, and that depends on, well, the fusion graph, and then a bunch of local weights, which are like the v and the h. So let me explain now how to connect the first two parts of this talk. Well, okay, so at every vertex I drew, I have two, so that's the vertex where the two lines might hit each other, and these are the two ways they can avoid with the two kinds of local weights, v and h. And the way I would draw this now in the fusion category language is say, take this graph, every time I stick in this, well, I then expand it out, and then sum over all loops, multiply by the appropriate local weights, and now sum over all the things. We expanded out, sum over all the possibilities. And this again is to evaluate the graph. And in this case, the evaluation, since it's a bunch of closed loops, basically the only thing you can have that's topologically invariant is count the number of loops. And so you get this number d to the number of loops. And again, since there's some stat mech people, for historic reasons, this d is n, and it's called the ON model. The historic reasons are good, but the name is kind of, and yeah, I see in the comments it looks like the Kaufman invariant. I'm going to get there, yes. So it's called the ON model typically in StatMat because it had something to do with models with ON symmetry. But here D is a continuous number. All right, so now let me explain a little bit more precisely how to relate the two partition functions. Remember I claimed you could, at the beginning, you could rewrite everything. So the k+1 objects are labeled by a bunch of, so these labels, remember I said finite number of labels. I'll take the physics convention for something related to SU2 and call it spins. Mathematicians use integers because they're more sensible. And so this is SU2 level K, which, well, people who know conformal field theory have heard of that. But from the category point of view, there's some objects. They're labeled up there. So it's like representations of SL2, and they have fusion rules like SL2, but we truncate them. So we stop them at K. And again, if you know some CFT, this is familiar from that context. But here for if we have 1/2 times 1/2 gives the usual 0 plus 1. So that's a fusion rule. And so now the way we relate these two pictures is the lines making up the loops get labeled by the object to have. And then when lines meet in a fusion category, I draw a picture. Remember I said before, if you have the identity, well, you can just omit the line. And now just to make it clear, I draw this squiggly purple line for 1. So I can do that. But now you have to remember something. This is where the power of things keep going on. So there's another basis you could write down. I could have fused these guys. So I have this. So this is one basis, the one on the right, and one on the left too. And so we now have two ways of doing this. And this is going to be the key to connect it to the loop model. In a loop model, we also have two choices, but we draw them like that. And so there's the two ways of drawing the avoid when two things meet. Now here's one way of doing it in the category, here's the other. But the F symbols relate everything. So what you can do, and I even wrote down the numbers there, you can see on the right, you can pick any two of these 4 you want and relate them. And the key is to not, and the key is you won't change the evaluation of your diagram here. So you can get the loops now. So let me, so maybe I'll do 5 more minutes and then we'll stop for the break. Does that sound okay to the?
Yeah, sounds good.
Okay, because then I can kind of get through then actually I'll be kind of through the basics, and then the next part will be about integrability. So good. Okay, so first of all, so here's the advantage of why I did this categories, because obviously counting loops is easy, but I made it much more complicated by drawing these vertices. But okay, one advantage of this is now I can do this for lots of different, basically any fusion category. You can define a lattice model and again define a partition function. And again, you have to evaluate these more complicated graphs, but we have the rules. There's these local weights there that I parameterize like that, but it's basically the same thing. And then you do that evaluation of that. And as I've already indicated, what Temperley and Lieb did, this setup gives you a general way now of relating local models to these global ones. And I'll say a little bit more about that later on. And you can, and what's the most important is I can derive new properties. And so there'll be the integrability ones, talk about it, and there's the topological defects they'll talk about in a second. So let me quickly then just summarize those 2 points I made, and then I'll quit for the break. Okay, so this is how you get the local models in this setup. Just generalizing what Temperley and Lieb and Couture and Castellan did. Well, the local degrees of freedom live on the dual graph to the fusion diagram. So they live there, and they take their objects in this category. So for the loop model, in SL2K, SU2K, it would be 0, 1/2 up to k over 2. But the point is, we can relate the local Boltzmann weights to the global ones. And these are purely local. They just depend on the F symbols. And this in the math world, they call shadow world. It's often associated with the names of Turaev and Vera. Kolya Reshetikin did some crucial things. Actually, Von Jones did too. Lots of people, these were classic papers of the 70s. Barrett Westbury also did stuff. There's actually other people who made fundamental contributions to this, but the partition functions are the same. And the category just hands you the answer to this. Once you set it up, you don't have to do any more work. And lots of models we care about can be written in this fashion. So that's the nice thing. Okay, so then one more slide before the break. Then now is the commercial for my paper with Dave and Roger. Another advantage, and what before, other than the stuff I'll talk about after the break, is you can make lattice topological defects. And so you can find exact on the lattice topological defects. So you move them around and you don't change the partition function. That's nice, but we can do a lot better. We can make them branch and fuse these defect lines, which in the brute force setups before really people didn't know how to do. This allows you to find lots of generalizations of Cramer's 1A duality. We can understand exact degeneracies in gap systems, one of our applications. You can derive these Affleck-Ludwig boundary G factors, and you can actually get exact results directly on the lattice, like dimensions of operators, which dimensions up to a half integer of operators on a lattice calculation. So it doesn't converge to the exact answer. You do an exact calculation on the lattice, actually an easy exact calculation on the lattice, and get, say, 1/8 for the dimension of the spin field. And I see. All right, so that, what's the next slide, I think is a good place. Okay, so next slide, I will then get to integrability in the next half and take a break. Or do we do, I forget if we do questions now or whatever.
Yeah, maybe we can ask a few quick questions before the break. And can I ask about the definition? So initially you have these loops. Yes, you have weights for loops for avoiding horizontal and vertical avoiding. Then you introduce this new class of pictures with blue intermediate line. So, and how is now, what is now the definition of this evaluation on such type of?
Yeah, good. So the point is, because it's a linear transformation between the bases, yeah, where there it was. Because it's a linear transformation, you would say, right, you know, I wrote before, there, A is my general notation for these. So there'd be A in front of that one, and, you know, and then this one. So I can express this one as a linear combination of these two. And so all you would do is just a linear transformation of the weights in front of the two avoidances in terms of drawing your
Okay. You use only as a definition, and it is just changeable.
Yeah, no, so yeah, you can look in.
Yeah, okay.
So yeah, no, so this is, and actually, let me put in a plug for a work I did a lot. If you're trying to do a quantum loop model, so where these things become, you know, vectors in a Hilbert space, then what happens is this is just a unitary change of basis in your vector space. So it's actually, in some ways, even more elegant in that setting.
Okay. And another new object which you introduced with heights. So does it satisfy nice properties like this fusion? So can you?
Well, so you use the fact that the heights are objects in the category to prove things like that. Where's the formula I showed? So this formula here. So it's all these manipulations. So basically, yeah. So basically, you derive bigger diagrams. You see pictures. We wrote it out in a lot of detail in the paper with Dave and Roger. So you see these. You basically draw more pictures, and then where these things are labeling things, and then you evaluate those things, and that's how you get these formulas. It's really. Yeah, I mean, it is sort of elaborate. That's why I just sort of flashed the formula, because it's simple in the end, but it takes a little work to actually show.
Okay, as a quick question.
Can I ask something? So by using this trick, you break a 4-point vertex into some 3-point vertices, right? By using this extra field in the middle, basically, right?
Yep.
And this looks very, this looks clear when you don't have spectral parameter for the external lines. Now, if I have a U and a V for the external lines, and then I have an auxiliary field, and then I want to break it, and I want the same U and V in the end, how will the external field carry that information? That in the end, I still need U and V.
That's kind of the topic of the remainder of the talk, although I probably won't give, I won't answer your question precisely, so maybe hear what I have to say. But yeah, basically what happens there, well, I'll explain, you know, how Yang-Baxter has this parameter. It's called the spectral parameter in that context, which in the scattering context becomes the rapidity, as you of course know, and then it follows along for the ride there. So we end up, so the point, oh, well, so I can say, actually, let me say, so, well, oh no, wait, on the slide, there's one more review thing, but this one's quick. The next topic was called Baxterization, and what it basically is the process of turning these fusion categories that don't have the momentum in there, or the spectral parameter in the lattice models, into solutions of Yang-Baxter, which does. So you see, notice in my Yang-Baxter equation here in the next slide, I've got those parameters there. So that's kind of the topic there is one of the values of my constructions gives you an easier way to see where that comes from. So I guess, yeah, thanks. That's a good plug for getting people to stay to the last part of my talk.
Okay, and now we officially go to the coffee break with camera off.
Okay, good.
Just stupidly. Yes, please.
Okay, so this part of the review, I'm going to go really quickly since it's an integrability seminar. The Yang-Baxter equation, the key thing to notice, like I said to Pedro before the break, is the Yang-Baxter equation has a parameter in it. So these Boltzmann weights, well, in the way I drew it, there's many parameters, but it turns out there's a special parameter. The reason it's special is because the Yang-Baxter depends on the parameter. So the Boltzmann weights depend on this parameter. We've got 3 Boltzmann weights, but notice there's only 2 independent parameters in this situation. And so the key thing to notice in the Yang-Baxter equation, also the triangle looks different, but notice U is up there now where it was up here. And so Baxter showed how you can use this to construct commuting transfer matrices. So you find Boltzmann weights that satisfy this equation, and then you can construct a commuting transfer matrix, Baxter's classic result. Just to flash quickly in the height models, again, the heights live there, and so the equation will look like this. And there's a sum on that side, and you sum over the center height on both sides. But again, the 2 are related by the thing I briefly described a few slides ago. So let me just write out the answer for, the Yang-Baxter equation. So you plug in this expansion over loops into the Yang-Baxter equation, you get a bunch of pictures, you get this horrible nonlinear equation. Notice you get a D in there. That's because when you do this, you get one of the configurations, you get a closed loop in the middle, which I can get rid of and make a D. Anyway, it turns out it reduces, even though it's a lot of equations, most of them are easy to solve or reduce to this one equation. And it's this horrible functional equation. There's 3 there, 1 in there, 2 there, and a D. But there's a solution, again, long known. If you take W, and so W is the ratio of H over V. If you take that, there's a solution, which now, again, this shadow world, this relation to local, this gives what are people call sometimes the RSOS models or Anders-Baxter-Forrester models. And these are the Boltzmann weights. So the loop model is connected to that. And that's, if you wish, a more modern way of saying the kinds of things Baxter and various the temporally did back in the old days. And so that is, but of course, I mean, one of the things that is just, come on, that's a really simple answer for something hideous, that hideous equation. So again, this hints that there's something else going on. So now, so let me tell you now, last review bit, and again, I'll go quickly because it's pretty easy. So let me say what Jones did back in there. So he showed, so to reduce his brilliant discovery to something very crude sounding, he showed that you could give representations of the braid group from the temporally lead algebra, which is exactly related to this SU2K category I keep talking about. And so what he showed is you can get a knot or link invariant by doing this. Okay, so it's a multi-stage procedure. You first project the knot and link into the plane, so you get overcrossings or undercrossings. And of course, to get an invariant, it can't depend on how you project. So there have to be rules. Okay, but what Jones says, okay, so to make the Jones polynomial, so someone mentioned Kaufman before, so this is where it is. So what Jones did and what Kaufman framed beautifully in this fashion was to say when you have an overcrossing, I replace it with this linear combination. When I have an undercrossing going like this, I replace it with that combination. I mean, it's to put an orientation on there to be able to decide which one is which. Okay. And then, so now this looks familiar. You take somewhere where 2 things hit and we resolve it into avoiding horizontally and avoiding vertically, or avoiding one of 2 ways. And then to get the Jones polynomial, you do exactly what we did there. When you have a closed loop, you get a weight D, which is there, but, or N if you like the other language, but in terms of these Qs, which is of course the quantum group Q, if you like quantum groups, is Q plus Q inverse. And that's how you get the Jones polynomial, almost. There's one catch. Okay, so to get a topological invariant, it has to satisfy these moves. And what happens? I'm gonna turn that off. So topological invariant, this is just sort of two overcrossings. Obviously, I can just drag that one over and get the same topological, same knot. And then, but you see under this procedure, I place this linear combination, I get 4. But then this one at the end has got a closed loop, which I can get rid of. But then remember, D was Q plus Q inverse, boom, 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 they all cancel. I get that. The third Meister move, yeah, so this is, this is starting to look familiar. So what happens, this one is just taking this guy and then dragging it through underneath. That's the middle one. So that goes underneath. So that's clearly a knot or link invariant, and it has to satisfy it. It's called the third Meister move. I'm not going to plug it in, but it's not hard to show. And of course, yeah, you see the resemblance. But here's the thing. So one of my pet peeves is often you will see nowadays, and even in the mathematical literature, people calling this thing the Yang-Baxter equation. It is not. It's the third Meister move. It predates Yang and Baxter by a considerable amount of time. And more crucially, it's not the same thing. Yang and Baxter did something more general. There's a parameter here. There's no parameter there. But the resemblance is obvious. And indeed, what the big fad, well, momentarily in the late 80s was relating these things. And what in the usual parameterization of the spectral parameter, you take it to infinity or I infinity, and then you get the braid and the unbraid or overcrossing and undercrossing. When I'm calling them braid, of course, you think of these as world lines of particles. In time, these are things braiding around each other. There's one subtlety that I don't want to dwell on because I'm going to run out of time, but the first Meister move is actually kind of interesting. So say I get something like that when I project my knot or link down into the plane. Well, obviously, again, topologically invariant in 3 dimensions, these two are the same thing. That's called the first Meister move. So your invariant has to satisfy it. But the one I wrote down doesn't quite satisfy that. It gets this annoying factor there, as you can easily see. So we replace this with a D, and you check, and that's why you get Q to the -3/2. Minus, do that. And the way you do is you have to frame the knots. You turn each link into a ribbon and you keep track of twists. When I do this live, I take my belt off to demonstrate this, which wakes people up, but it's not kind of weird to do this in my bedroom, so I won't do that. Anyway, so now again, you can fit all that, this last bit that I said, into the structure of the tensor category. And you need some more data now. So before I was talking about fusion categories, now I have to add braiding. And here's the braiding there. So if I have this now, so this is a little more complicated. Again, I put labels as opposed to what I had before with the last few slides. I put labels, and again, I untwist that, and I get this factors here, and these are related to the spin. So that's called the spin. And then these are these twist factors. These news are these examples of the annoying things that I got rid of, called Frobenius Schur indicator generally. So I'm just going to ignore them. They're there, but again, you can keep track of them. And they just waste a lot of your life if you screw up. So anyway, so again, it's saying what happens to the twist. And so again, this is what, if for those who know something about anyons, this is how anyons behave. So you get a factor when you twist by 2 pi. It's the quantum mechanical spin. Sorry, I'm only twisting by pi here. So they're only going around by 180 degrees. And so actually now you can that's all. I don't have to specify braid matrices. I can just use this twisting, at least in the categories that with the simpler properties that I've said. So in other words, if I take this, I then do an F move and get that. And then I untwist and get that. So this, if you wish, this thing here is the braid matrix, people will call it. And so it tells you again what happens. So again, there's no parameters. We haven't gotten the Yang-Baxter yet.
Sorry, where was the information that blue line is going over the red line?
Yeah, you're right. That's the way you think about it. So put it in 3D. But the whole point of all this category stuff is we take this 3D thing that we project it down, and then we still do these manipulations. So in order to do the 3D, we need more data. That's why we need this braiding on top of the fusing to turn this into a number.
Okay. Sorry, just to make sure. So now the F numbers are not independent; they are related to previous ones.
Yeah, these are the same.
Right.
Sorry, what the F? Sorry, I didn't. Can you say
so this F quantity is the one that you called F before. Now they are not independent. Now they are just expressed like.
Yeah. Oh, I'm sorry. Yeah. So right. Thank you. I did something special. So notice I did an F move where there's an identity in between these two. So that's how the F move did there. So if you think about it, what I was doing is I have B and C, and then with an identity in between them. And so then I fuse them to that with an A. So that would be sum on F there. But I use something which I didn't tell you about, is that F simplifies to that. Yeah, thank you.
Oh, okay. Thanks.
Yeah, sorry. No, I was going too fast. So good. So that's how you do that, and then you get that. So that's this is an F. I made, yeah. All right, good. Now I can get to the heart of the talk. Sorry, we thought of like 15 minutes to go, so maybe 20. Okay, so this is Pedro's question from before the break. So Jones, people made these connections, but the arrow went originally the other way. They say we have all these great solutions to Yang-Baxter because we work really hard, and the integrable people do all this great work. How can we now go backwards and find lots of not in link invariants? So there are a bunch of papers where people found not in link invariants. But Jones said something that was really interesting. He said, let's try the converse. Let's start with the not invariant and then try and find solutions of the Yang-Baxter equation, and hence a lattice integrable model, or perhaps an exact S matrix if you like those. Well, that equation is kind of nasty. So it'd be trilinear in those Boltzmann weights. Now, some success in some I think sadly neglected work. People did actually do some fairly gruesome but impressive calculations using quantum group algebra. So Jimbo set out like a procedure, and then Australian group, Zhang, Gould, and various collaborators came up with a way of solving this. So they did find lots of solutions systematically. You can obviously do this by brute force, but they did come up with a fairly systematic way of doing this. But if you look at their papers, they're very technical, and you have to know something about quantum groups to delve in it. But then when you get to the answer of these papers, the quantum group is barely involved, to be honest. All in fact you have is some quadratic Casimirs of original Lie algebras. We don't even really have the quantum group at the end of the day. So obviously, I'm sure they noticed at the time, but they didn't have any ideas on how to go on. It does suggest there's a much better way to turn fusion categories into solutions of Yang-Baxter. And so that's what I'm going to talk about. And that's a method that, well, seems to work for Baxterizing. That was Vaughan's word. All right, so here's the answer. Since I knew I'd be running late, I wanted to tell you what the answer is, and then I'll spend the rest of the talk telling you how to do it. So again, so I drew this picture before. This is now the general version of the crossings and the avoided two kinds of crossings in the loop model, and sum over all these graphs. So these things are these amplitudes or the local weights. So these are the local weights. And what we're saying is, in order to get a fractional spin conserved current, and I'm going to tell you what that is, then the Boltzmann weights must satisfy this property, at least in the case with my simplifying assumptions. And that's really simple, where omega is that twist factor, e to the I pi times the spin, and that's it. That's all that there is.
Sorry, Paul. So essentially, the conservation of the current itself implies the constraints on the weights, right? Which you show here.
The current.
I mean.
Oh yeah. Well, so I haven't explained the currents yet. So I'm just that's an advertisement for the rest of the talk.
Because I was sort of thought that you are making the statement that the scheme goes the other way. I think that okay.
Right. So okay, let me explain the logic. Okay. So good. Yeah, I didn't quite get through all the logic yet. Okay. So I say this is just a definition here. What I'm telling you is, okay, I can define these models. So this is just the thing I've circled is just a definition. Okay. What I'm saying, if you demand a fractional spin conserved current, which I haven't told you what it is yet, but I will, then you find that the only time that admit this fractional spin conserved current is if these obey this. And the key thing about the fractional spin conserved current, it's a linear condition on the Boltzmann weight. It's not trilinear like Yang-Baxter. And then, so I haven't solved Yang-Baxter, but all known examples of this thing that I know of, and there's many, they all also satisfy Yang-Baxter. Yeah. So it's not a proof that these are solutions of Yang-Baxter. But so that's
probably the second point. Okay, I can postpone. I was wondering also if there is a counterexample.
No, not that I know. So far, so good. All right, so let me explain what a conserved current. This is this beautiful, again, sadly neglected paper because it was already the 90s by then and people were ignoring this stuff. But Bernard and Felder gave a quantum group way of thinking about these things. And then they wrote down this equation. So now a conserved current is going to be this thing. I'll say a little bit more in a second. So think of it as some non-local object. If you know the Ising model, you can think of this as the and then you get the local weights. So this slide is purely review. Okay, so now I'm going to define the currents in my setup after going to all this trouble. So we pick another object. Okay, so first the legs are all labeled by this row. So I didn't draw it in this picture, the big picture here, but all these are labeled by some object row. It's 1/2 for the vertices. Okay, and then you sum over all the intermediate ones. So that was in the previous slide. Okay, but now I stick in 2 extra things and do the evaluation. So I do the partition function in the usual way, but then I stick in another string going from there to there, and that's labeled by another object. They don't have to be the same object. And to connect for a second to the stuff I do with David and Roger, this thing is a topological defect, and this is terminating a topological defect. And that's the way you define a current. I need the braiding in order to go over the middle. So you think about, I just take the thing out of the plane, and that's how I define there, and then the vertex. But now I do the same thing. I just have a more complicated graph. There's just a guy connecting from there to there. And there's one catch, that stupid braid factor I told you about comes in, because if I have this kind of configuration, in other words, if I'd started that one and gone that way before going over, well, I can get rid of it by that twist, but it's gives me that factor. For some unknown reason, I put an inverse there in my definition. So that's the definition. But the point is that once I say this, I'm done. I mean, this is a unique object within the category, within my rules. And then all the local Boltzmann weights, the A's are at each vertex. It's all good. And just to give the example in temporally Lieb, these, remember I said the lines were labeled by 1/2, and we have these ones. I draw it as a squiggly one here, but I'll draw it as the dotted thing. So I just connect that there, and that sounds very complicated, but in this case, it's really simple. If the thing will vanish unless the green line is connecting the same loop, and I think I drew it, so notice that's all the same loop. So that would be non-vanishing. That one goes all the way around. And if you remember long ago, when I defined these things, this has to be a function of delta AB, so that has to vanish. And that's why they have to be on the same loop. So, you know, the one thing you can't forget is this twist factor, though. So that still matters. It has to be there. If you just say, let's forget it, you won't get anything useful. All right, good. Since I'm running low on time, I'm only going to say a little bit about this, but I definitely want to make contact with the literature. So these, you know, again, people reinvent the wheel many times. This was a whole thing in the, was it sort of somewhere 2005, that era, where Smirnov was trying to generalize his amazing work on proving rigorously that the Aasen model is conformal and invariant. He was trying to generalize that to other models. And he started discussing these conserved currents, except he didn't call them conserved currents. He didn't think about this way. He called them discrete holomorphic operators. He wanted to prove that they were holomorphic in the continuum limit. But it only really works for Aasen. But in the course of this, people came up with a bunch of examples of these operators without really making the connection to the work of Bernard and Leclerc. As far as I know, historically, we talked about history for a second. It came because I gave a seminar on this a long time ago, and Denis Bernard was there and pointed out this paper, which nobody in the room, including me, had known about. So anyway, but they had done all this, not knowing about Denis' paper, finding these things. They were looking for, instead of thinking of it as a vanishing divergence, they thought of it as the lattice, half of the lattice Cauchy-Riemann equations. And then Carty said something different. Okay, so it didn't really work for what Smirnov wanted, so he moved on to other stuff. But Carty made this observation that I said, well, when you find solutions of this thing, if you think about it not as a condition for the conserved current, but you think about it as a solution for the Boltzmann weights, it's linear and solutions all satisfy the Yang-Baxter equation. So that's what it is. So let me show schematically what it is. So this is now the conserved current relation in my picture, the thing Bernard and Leclerc wrote, but with more labels and more fancy stuff. It's just simply that, you know, these are the two in and the two out. Or if you move to the other side, it's a vanishing divergence as you go around to square. So that's the thing. But the thing is, in the category, all of this stuff is known. That's why I like it. But now what Smirnov said, yeah, okay, Smirnov was interested in certain integrable models that became CFTs in the limit. And he said, oh, well, let's look at these objects because I can maybe think about CFT operators by doing them. So that's what he did. Carty said, think about this equation the other way. Let's not determine the amplitudes here on the thing. Let's not determine them. Let's leave them variant. Let's just ask, can I define models such that I can find a solution to this equation? Forget Yang-Baxter and all that. But what he showed is if you solve this equation for the Boltzmann weights, and this is linear in the Boltzmann weights, in the A, in the local parts of the Boltzmann weights. Sorry, when I say Boltzmann weights here, I always mean the local parts in this context. It always solves Yang-Baxter, the statement I made a few minutes ago. And so now, what I keep saying, everything's defined in the category. So lots of examples were worked out by Carty and collaborators. Oops, I put it on all the list people somewhere. And Smirnov and collaborators too. But I can just get many of them. You have to generalize the equation to the more complicated categories to get all of them. But anyway, so I just plug this thing in to the conserved current relation, the thing I drew on this slide. I manipulate all the graphs. So you see here.
Paul, I'm still a bit confused by something very basic, probably, which is normally we think of the spectral parameter as attached to lines, not to vertices.
Yeah.
And can you just comment a few words on that? So in that picture, for example, what if I don't want to put a U, but I want to put a U1 and a U2 associated to the two lines? Then how do the pictures keep track of this U1 and U2? Because
no,
when the particle splits, how does it know that before, when, right, you merge into a wiggly line and then it splits again? How did this splitting keep track of the merging that happened 1 year before?
Yeah, sorry, I shouldn't have gone so far. There we go. this is, the two things are not the same. So, and where they connect is because of Yang-Baxter. Because if you take the Yang-Baxter equation, so I'm labeling these by U's, which is the way you do it in a stat mech model, right? The U is a property of the whole square, if you wish, in the face in Baxter's thing. That's a property there, or this is the midpoint of the face thought. But the point is the condition on the Yang-Baxter equation, because notice this plus this, the U plus U prime. So I can assign a theta, if you wish, there, theta 1, theta 2, theta 3, where U is equal to theta 1 minus theta 2.
I guess Pedro's question is what to do in situation when our matrix is not a function of difference.
Oh, is that what you're at? Oh, so you knew this? Okay. Well, maybe other people didn't. I was going to say, I was surprised you didn't know this. Yeah, they're called the Chiropods models, and I'm obsessed with them, and I would happily talk to you for hours about the Chiropods models, but not in this talk. So yeah, there are known examples where they don't satisfy the difference property of solutions of Yang-Baxter. Sorry, gave a long answer to. Is that what you wanted, or?
Yeah, it's related to that. Yes.
Yeah. So, but as a general principle, your question is a great one, because I mean, there are different things, and after I can tell you something about, I'll make a comment at the very, very end about this question too, because this back and forth, because the things are not the same in all the pictures, there are issues, and I can tell you something interesting maybe after the talk if you want to stay on about this. So no, this is not a solved problem.
Okay.
Anyway, so all right, so the category I keep saying is that it hands you everything.
Maybe
so,
just to make it more precise, for example, for the Hubbard model, right? It's not of difference form.
Well, that's right. Hubbard, well, that's right. Hubbard not as well. That's right. Hubbard, yeah.
So would Hubbard have would it be possible to find our matrix of Hubbard through these currents?
No. Well, I mean, not immediately, because but we haven't thought about this yet. Hubbard is really Hubbard's strange how simple it is in some ways. It's really nasty from the integrability point of view, as you know. I don't know. Question for the future. Yeah. So, yeah, there are many cases where I know that, and conversely, there's categories that I know where I don't know yet. We're working on it where I can go the other way.
Maybe another question. So there's also this recent works on understanding the spectral parameter by Kevin Costello and collaborators, right? Where you also, so you go from Jones Polynomial to Schoen-Simons, and now you promote Schoen-Simons to this 4-dimensional thing. Does this green line have an interpretation in that?
I have some babble on that. I've talked to Kevin at length about this, and we're mutual agreement that the two things have something to do with each other. I can babble about that. But since it's getting late, so let me finish the talk, and then I am happy to babble all evening about this stuff. So yeah, we can just let the people go away. I mean, I really am basically done. What I was saying before the excellent questions is I take each of these and I can do F moves and manipulate it into this form. So you see on the previous slide, for example, here's a nasty one where I manipulate this around, but it can be done. Everything is known from the category. The only thing that's left open are these constant factors there, the mu's, and these amplitudes, which I've left arbitrary. So this then becomes an equation for these things here. And of course, if this is going to be 0, each of these are linearly independent. That's why I find the common form. That's why I need the F moves, because these are not linearly independent, but I reduce them to a linearly independent basis, which I chose like that. And then it has to vanish for each element of the basis. And the remarkable thing, you have solutions, the thing I wrote there. And that's a general thing. The F symbols cancel. That turns out, so Tobias Eisborn has been thinking about this in more general. So he went over my laziness in simplifying and did the harder work, and also showed, well, a variety of things. But among them, the F symbols only cancel in this simple case. So it's a much nastier equation. And the solution's much more complicated in general, but here it beautifully simplifies. So that's really it. There it is. It works for any braided tensor category. I think I probably need some for if there's any category people, you really need a little more structure. It's called a ribbon category. But no quantum groups ever appear. And the answer, and this sort of explains why the quantum group answer ended up so simple, is because you don't need quantum group representation theory to get this. It follows from what I think are much more basic things. Now, you don't always get a solution. In fact, to say generically, you don't. You have to check things are consistent with the fusion rules, the braiding. There's stuff in my paper you can see on how to do it, but most definitely not all that. Oh, I don't know why I put this in. These are the people who found a bunch of solutions, though, but we can reproduce these solutions in this setup. And like I say, someone asked before, all known examples satisfy it, but maybe that's the drunk under the lamppost. All the cases I did were the kind of nice ones, and maybe we want to get to some nastier ones that won't work, which would be really interesting. Okay, so that is it. This is the conclusion slide. So general criterion was just saying, I'd like to know when it works. I'd like to prove that it always gives a solution. I don't know if the first one is even true, but so the Kevin Costello question. Everything I've got, these always turn out to be what are called trigonometric solutions, the Yang-Baxter. But if you look at what Kevin does, it's very much related. Kevin has a framing anomaly, which is very much like, in fact, it is basically this twist thing I told you. And I have a very glib, but I like it, way of saying is what I'm doing here is you're adding geometry to topology. So the category is topological. And then I'm adding some geometry to it by worrying about what happens with these twists, and then what happens these things. So this interpretation of the question I was answering for Pedro, what happens with the angle dependence there, and that's adding geometry. And so that's just BS, but I think it's good. And I got this question before earlier, the supersymmetric cases, supergroup cases. Can you relax that? Let me just say two more words and then quit about this. There's categories that aren't braided. Hagerup is a famous one. Half E6 is another one, the even part of E6. But there's this thing called the Drenfeld Center that it's called the double sometimes. It gives you a more complicated category where you do have braiding. That was kind of the key to what I did with Dave and Roger for the topological defects. So if we could find solution Yang-Baxter these would be new, and not just new in detail, new in style solutions Yang-Baxter. So we're thinking about that a lot, but I don't have any results yet. So again, sorry for running a little bit over, but thank you.
Thank you, Paul. Let's unmute ourselves, and thanks, Pauline.
Thank you.
And now we have time for questions, comments.
Can I ask another basic question? So is this useful for computing partition functions, say? I mean,
so
can we use this as a computational tool for computing things that before we could not?
Well,
like some partition functions with different boundary conditions or something?
Excellent plug for my other paper. The other paper is because these things end. So then these objects really will depend on the locations. They'll scale, they'll fall off in a conformal field theory, as 1 over z minus w to some power. But in our topological defect paper, and in one that I keep nagging Dave for us to write, like you let these defects just go around, so we don't terminate them. So forget what I talked about today. You let these things go around, and then you can compute these partition functions. Yeah, and you can prove all these exact. That's how you prove these exact things about the lattice, because I can do I can wrap defects around, and then I can do modular transformations, and then manipulate the defects back again. And I can do this exactly on all the lattice. So I cannot compute the partition functions explicitly. I mean, in the lattice models, you can never do that except in free fermion cases anyway. But we have an exact conjecture, for example, that relates lattice partition functions to continuum ones, and you can check it by for example, computing the eigenvalues of Dane twists, and those you get right and all this stuff. So yeah, so it's very useful. So it gives you an exact way of relating lattice to continuum. So we don't prove. So it's in the spirit of most of what SLE does. So we can do exact calculations, rigorous and exact calculations on the lattice. We can't prove it has a continuum limit, but you can state if the model has a continuum limit, then it must have these properties. Because it's true for any finite lattice size, must be true in the limit if it has a limit. So we can do lots of stuff like that. So not so much this talk. I have another talk on that. This talk today is more on I figured for the Integrability Journal Club, I should talk about what it has to do with integrability.
So these currents, just something very basic, so I understand. So these currents are like the discrete version of these Yangian conserved charges. Is it true? These higher conserved charges in the lattice, they would become these currents that you define?
Sometimes. So what they're more like, yeah, I mean, so a closer analogy, if you were doing icing, this thing would be like the fermion zero mode. Mm-hmm. So you do icing with appropriately twisted boundary conditions. It would be like the fermion zero mode. You sum, the charge would be the sum over the, so this thing is the fermion, and you take the equal amplitude sum all the way around the cycle, it's the fermion zero mode.
And why do you think something so specific should be general for all integrable models? This looks.
Why do I think? Well, I don't know. I showed it's true. So you can show, I wrote an unpublished paper a long time ago. You can do the same thing for parafermions, for example, and even in this Chiropods model that I love.
Mm-hmm. I see.
So,
but it's not obvious to see it as a consequence.
Yeah, it's not at all obvious why for the Fibonacci model, the people like to call it golden chain. It's true. It's there.
But would you be able to argue that, for example, for these models that are not of difference farm, that something like this should also be there, like Hubbard or like these chiral models you were talking about?
I simply don't know. Honestly, I don't know. And Kapustin gave some version of this talk a long time ago, and he says in a way it's kind of a, well, to generalize slightly what he said, it's kind of a no-lose thing. Either it will work, which will be interesting, or if it fails, then you'll have a way of detecting the difference between Hubbard and other, you'll have a clear criteria to identify, okay, Hubbard is not like a quantum group model because, it fails this test, whereas, all quantum group model, all integral quantum group models, I'm sure this will work for. So it'll give you a way of detecting quantum groups, and that would be pretty interesting too, maybe even more interesting. So either way, yeah, so we don't know. We haven't tried Hubbard. Hubbard frustrates me in many ways. I have to spend time on Hubbard, but anyway, that's why
you might know, but Hubbard is interesting for some people in this audience because the R matrix of Hubbard turns out to coincide with the S matrix of the spin chain that appears in ADS-CFT.
Yeah.
So that's one reason why people are interested often in the algebraic structure of Hubbard in
that's actually
more high energy context.
So yeah, that's why, so many smart people are working on this already. Please do it. I'm old enough now that I don't feel the need to please read my paper and do the calculation. No, it'd be great. It's an excellent suggestion. I hope someone in the audience does it, or you, or come ask me. I'm happy to answer as many questions as.
Sorry, Paul. I think maybe I was just having a point related to what Pedro was asking, because just thinking that even from the perspective, I'm talking about regarding this relation to the that YB in principle in this categorical language doesn't need to be an additive or whatever non-different spectral form as you have been shown. But I was just showing that I think there are axioms at the axiomatic level, for example, from the graph theory on multigraphs, that no matter how do you assign either vertex or edges, there is a translation. There is a translation map between these two descriptions. The second question, of course, is how does this reflect the underlying whatever quantum or Yang-Baxter algebra? But I think it is doable. Maybe Kapustin was mentioning something like this. If you can elaborate on this.
Yeah, well, to answer your first question, that sounds. I have nothing to say other than that sounds really interesting. Someone should explain some of these results to me in more detail, because that. The second is no, I to actually prove. So I should have said in the quantum group case, they can actually prove it satisfies Yang-Baxter. So I said, you know, so yeah, I was sort of saying, well, their solution didn't require all this, but to actually prove that the thing they get satisfies Yang-Baxter, they need this quantum group apparatus. So one clearly will need some more, and you can just kind of see you need more structure. So again, then so I don't have an answer to your question. I guess then the question is if we can find examples that are integrable from this procedure, then that hints there is some other structure out there that generalizes the quantum group structure to go from this to that.
Exactly, because like Pedro mentioned, this 1/1 case of this ADS5 integrable spin chain, which is essentially a Hubbard model, was which was mentioned by Meister. But there is also ADS2 and the ADS3 sector spin chains, which also are of interest and possess non-difference form dependence.
Yeah, yeah. No, it's you know, I declared victory. It took me like 8 years to write this paper last summer. So I think basically I decided personally, I was not going to think about this for another. But I started with Tobias. So I think your strategy is a great one because that's not one I've tried. I'll say my strategy is I'm picking some categories I know about and seeing if I can find an integrable model. You're saying, well, we know, maybe even a better one, start with some integrable model we know about that isn't nice like this, like the quantum group one.
It's sort of Descartes' way.
Yeah, yeah, no, exactly. So no, I think then you're Smirnov's way. Whatever. Yeah, but no, I think that's a great approach. That's why, well, I'm happy people are interested in. So yeah,
it actually can help if you show how to derive a trigonometric solution, like 6-vertex model. I mean, what numbers should I put around, and what equations to solve to get 6-vertex matrix?
It's well, yeah. If let me do it in the. So let me think. So let's see. Well, it's okay. So right. So let me just try and do it schematically. So 6-vertex model actually turns out it's tricky. It's easier to do it for the critical line in the 8-vertex model, but at least easier in my setup. But the point is there. So the first thing is this equation is really nasty, horrible in terms of the heights. I think I had a slide which I kind of, so the heights will live here, you know, on those things there. And then you're, so this sort of weight for this is given from the category. So that's or from Dave's and Rogers in my paper or whatever. And then this one is, you know, the usual Boltzmann weight kind of thing. I guess it would be that. And so it's horrible to write out. In fact, as a exercise, so for this Fibonacci case, the golden chain or the A4 RSOS model, the Trescher-Ising lattice model, you find if you do this by brute force, I think it was 11 equations and they were all completely different. I mean, so all I could do is, I knew the solution from this, but all I could do is plug in. So it's horrendous, but you literally just have a Boltzmann weight. You have these factors that come from the category, and you just manipulate them like I did. I guess that was the previous, you know, do things like this. It ain't easy. And that's why I mean, and so doing it by brute force is this nightmare, but if you know what these things are, the category hands you all. So it's easy with the category. By brute force, it's impossible.
But can you at least specify data that you have to supply? Like what K belongs to which set, A belongs to which set?
All the data for these simplified cases, for, you know, when you have more complicated cases, all the data you need are just the F symbols. Okay, so let me start with a simple one here.
No, but no, okay, I don't ask what they're equal to, but okay, I want 6-vertex model. It's the simplest one I know. So simplest, I mean, which data do I need to derive it? I mean, maybe not equations, but just data.
Let me do Ising. So Ising, you have to do the height, so Ising is a local model, right? So, because the pictures are easier, I've been drawing there. So Ising, there will be spins, say, here. So this is a plus minus. That one will be minus plus because that's a spin flip defect in Ising. And then this one will be a plus or minus there. Okay, so that's the data. Ising's easy. These things are kind of a nerd. If you know anything about anyons, you would put a sigma there. Okay, so these are the things. All right, these. So what you would do now is these are known for Ising, or these labels. So you then now have to kind of remember when I changed over from heights to from these loops to heights, I get like that. So that's a Boltzmann. Could draw the Boltzmann weight like that. And then there's numbers for each of these things. Remember these amplitudes that I wrote. Okay, and this says now if I do this manipulation, I get this graph. And so this is all the data. And all of this data here is just given in terms of these F symbols there. Because I define the lattice model as fusion category. So the only way the braid stuff comes in is by this kind of stuff. So that's real. I mean, so you look at my paper, maybe the better answer is look at my paper and you'll see that I wrote out all the data there. There's really not that much data. But the nice thing is to do it for the height models, you don't have to write out you don't have to write out all this stuff I put in red there. So let me erase this. All you need to know is this, and that's the beauty of this. So if you start with the 6 vertex model, you rewrite it in this form, in this loop form, this non-local form, with the squiggly lines and all that. And then really all the manipulations you need to do are written here. So that's all. And so if you wish, that's why I was, in reply to the previous question, this is why I was going in this direction, because when I know a category, I know this. And then I go on to try and do Yang-Baxter. If you're doing with Yang-Baxter, you would have to do these things, at least naively, by brute force. Although maybe you guys are pretty smart and good at these things, so maybe that's not so. People have thought about Hubbard a lot, so maybe there's a way. So yeah, but really, I've hidden lots of transformations, but at the end of the day, everything on this slide here is really all you need to do. It's really that simple.
So excuse me, Paul. So thanks for the great talk, but I have a question about this. So do you really need the braiding of your input category here? Because it feels like the only objects that you need here are basically the anyons in your full theory. Well, and this is the Drenfeld Center. So I'm not a bit confused why you require that you need braiding.
Well, but I need braiding. I mean, just so I can draw the line over. You're right. So the Drenfeld Center hands you the braiding. So the point is, so to define these things, I need to go to the Drenfeld Center. So the open question, what Tobias and I are trying to understand is, can we basically use the Drenfeld Center? I mean, that's in essence what Dave and Roger and I is, and of course what you're doing in your stuff too. It's saying we start with a category that doesn't necessarily have braiding, but we take the braiding from the Drenfeld Center because it's there. And of course, that reduces to what I talked about, because the braiding, if your category is braiding to begin with, well, the Drenfeld Center braiding is just the usual braiding, So is that what you were asking? I mean, that's.
Well, indeed, it feels like it should, what you do should be valid also in this more general case. Where
it feels like it too, and that's what we're trying to do.
And all the equations are known. It's basically these tube algebras. No, you know exactly what all these objects are that you have to, all these tensors that you have to put there.
Yeah, I am highly optimistic that at least for half E6, this will work. I can tell in even more detail what Tobias and I've done. But
there's even more simpler ones. No, there's like S3. S3 is also has no braiding.
Yeah, I mean, some of them have braiding that's so obvious. It's sort of obviously true, but it's kind of cheating because the braiding is, I mean, it's still kind of, there's some quantum group lurking there. That's maybe kind of true for half E6 too. But anyway, I think it should work. Or like otherwise, or it'll be a detector for the ones which would surprise me even more. So then hopefully we'll have some new integrable lattice models to brag about next time I give a talk.
I have a completely different question also. So if you have Yang-Baxter, you basically require that these three tensors in your equation are the same. Or you have u, v, and u plus v. Yeah. But in principle, this u plus v, the intertwiner, can be a completely different object, no? So why?
Oh, yeah. So sorry. No, I mean, obviously you can generalize that. And in fact, even there was a bit of that in what the quantum group Gould and Zhang did. So yeah, so you can generalize that, and that's long been known in integrability. So
and which objects are these then from your category point of view?
Well, you would just then, so in fact, oh good, this picture is perfect. So instead of having a label row there, I would have different labels there. I would have row and call it row prime there, and then do the same stuff. I haven't looked at them. Another thing you can do, which some of the solutions that Cardy and crew did, were to take this to be not a simple object. So you leave vacancies on edges, for example. So they worked out a bunch of examples like that. So there's a whole bunch of stuff you can do that I just literally in the name of simplicity, I abandoned. That stuff all works.
I remember there used to be difficulties. I remember this looks like the tensor product graph result, for example. When chi had multiplicities, then you have various matrix structure.
Yeah, so that's what Tobias and I are mucking through now.
So do you have a construction in the case when there's degeneracy or multiplicities? I'm just curious.
Tobias derived the equation, so we have the equation, and we in one case S3 or A3, no, A4. Sorry, A4, which S3 is a subgroup. Rep A4, we have a solution. But we don't really understand what it means yet for technical reasons that I can bore you with later. So yeah, so
solutions have been found, of course, for
Yang-Baxter. Yeah, this in fact, yeah, the example we have there's this Jimbo, the Kyoto group, the very last paper they wrote, they had an example of this, and that relates to what we have. I haven't sorted out the details yet.
Okay.
I think because we have something more general than they do, but they also have something more general than we do, which is of course there's more that we need to figure out. It's so far it's very curious though, which is why we've delayed. We need to get back to that.
Okay, so I would propose to thanks Paul again and finish the official part of the talk, and then we can proceed with further questions again. So thanks, Paul.
Well, thank you so much.
And let's turn off the recording.
Well, I can kill the slides. I'm happy to sit and chat with anyone who wants to chat.
Paul, you are host now. Can you stop?
Who is the host? I'm the host.